Hi, my name is Yuliia Semenova. Currently, I am a leading researcher at the Institute of Geophysics of the National Academy of Science of Ukraine. Today, I am happy to present our study Seismic Hazard Assessment in the Shamkir Mingachevir reservoir region through ground response analysis. Seismic hazard parameters at a site not only depend on earthquake magnitude and the distance from the focus of an earthquake, but also on the surface geology. Surface geology can significantly worsen damage. These local effects, known as seismic site effects, can cause significant modification in amplitude level, spectral content, and duration of ground motion. These effects may increase the seismic hazard level even in areas with moderate seismicity. You can see an example of the Michoacan earthquake of 1985, where peak ground acceleration were higher in a city at a distance of 400 kilometers from the epicenter than at the epicenter itself. This happened due to the resonant amplification of ground motions by local soil. This example shows us that it is very important to predict seismic site effects before an earthquake occurs. How can we account for the seismic site effects? The most reliable approach is seismic ground response analysis. In total, there are three different approaches to ground response analysis: linear, equivalent linear, and nonlinear. Depending on what type of behavior of the soil material we are considering under earthquake loading, we call it linear or nonlinear ground response analysis. When we assume a linear stress-strain relationship of the material, we call it linear ground response analysis. When we assume it as nonlinear, we call it as nonlinear ground response analysis. Within nonlinear approach, there are two cases. One is equivalent linear, another is absolutely nonlinear. Depending on the magnitude of the expected earthquake and the ground conditions of the area, one or the other is used. Using equivalent linear approach, soil behavior is approximated as a Kelvin void solid. Then the equation of motion for a viscoelastic medium has the form 3. To take into account nonlinearity, we use an iterative procedure. On this slide, you can see the algorithm of this procedure. This procedure calculates values for shear modulus and damping ratio that are compatible with the strain induced in each sublayer. This algorithm is used by Prosaic, ERA, NERA, DeepSoil, and other similar programs. In regions prone to seismic activity, assessing the seismic hazard of hydroelectric power stations is crucial for maintaining the dependability and robustness of critical infrastructure. In this study, we investigate and compare the seismic response of near-surface soil at the Shamkir and Mingachevir hydroelectric power stations in Azerbaijan when subjected to earthquakes of different magnitudes utilizing equivalent linear approach. This analysis not only enables a direct comparison of the sites, but also facilitates the identification of underlying geological factors influencing their seismic vulnerability. At the first stage, we analyzed the seismicity of the study region according to the US Geological Survey. On this slide, we see earthquakes from 1973 to 2023 with a magnitude greater than 3. The left figure illustrates the earthquake magnitude distribution of the study area. The right figure displays the depth distribution of earthquakes. The earthquake magnitude distribution shows that most events in Azerbaijan occur with a magnitude of 4 to 4.5. This is almost 42%. The depth distribution analysis underscores a predominantly crustal nature of seismic events in Azerbaijan. Nearly all earthquakes are concentrated at depths of less than 50 kilometers, with the majority occurring at depths of up to 25 kilometers. This pattern suggests that the seismic activity in the region is primarily associated with crustal tectonic processes. To apply the equivalent linear approach of ground response analysis, We created simplified models of the upper 30-meter layers for Shamkir hydroelectric power station and Mingachevir hydroelectric power station. The slide shows a map of the average ground shear wave velocity of the upper 30-meter layer. Already from this map, we can identify vulnerable low-velocity areas. This slide shows changes in peak ground accelerations during the propagation of seismic waves from the bedrock to the surface through the upper 30-meter layer of soil at the sites of the Mingachevir and Shamkir hydroelectric power stations. Changes in peak ground accelerations for different amplitudes of input motion are shown. From the results we see, at the surface of both stations, the peak ground accelerations of the input motions increase. On the surface of the site of the Shamkir hydroelectric power station, peak ground acceleration increases more sharply than on the Mingachevir hydroelectric power station site. We see that, in general, in all cases, peak ground accelerations at the surface are roughly twice as large as at the bedrock level. On this slide from the Fourier amplitude spectra, we see the difference in the amplitude spectral content of seismic motions of the bedrock and the surface for input motion amplitudes of 0.19 G and 0.33 G. On the surface of the Mingachevir site, we observe amplitude amplification at lower frequencies compared to the case of Shamkir. On this slide, we also see the Fourier amplitude spectra of the bedrock and the surface, but at smaller input motions amplitudes of 0.05 G and 0.1 G. At smaller amplitudes, the amplification trend is the same. On this slide, we see the transfer functions of the soil profiles of the Mingachevir and the Shamkir hydroelectric power stations. We see that the transfer functions are generally similar, but we see peaks at different frequencies. Peaks at these frequencies indicate the potential for resonant amplification of seismic motions reaching almost 7 times. These graphs illustrate that the soil at Mingachevir hydroelectric power station amplifies seismic motions at lower frequencies compared to Shamkir. In the Mingachevir hydroelectric power station site, the worst-case scenarios are expected to be associated with low-frequency seismic motions, while in the Shamkir site, more unfavorable scenarios are expected to be associated with higher frequency seismic motions compared to Mingachevir site. Conclusions. The studies highlight the significant role of upper near-surface soils in affecting the dynamic of seismic motions as they move from bedrock to the surface. Soils with lower shear wave velocities absorb more seismic energy, resulting in lower peak ground acceleration at the surface. Soils at the Mingachevir station with lower shear wave velocity values compared to Shamkir exhibit resonant peaks at lower frequencies, indicated that soil softness dampens high frequencies while enhancing low frequencies. The amplification of low frequencies, up to 10 Hz, by certain soils can cause severe structural damage to most buildings due to resonant effects, as buildings typically have natural frequencies between 2 and 10 Hz. This emphasizes the importance of considering site-specific soil characteristics in seismic risk assessment and buildings design. Thank you for your attention.